Greetings, AP Chemistry students. Today, I'm going to pick up on this slideshow on chemical equations with where we left off yesterday. All chemical reactions have to be balanced in order to demonstrate the law of conservation of mass. You should know this by now. But in addition to just a normal chemical equation, we can write what's called an ionic equation or a complete ionic equation, where all soluble ionic compounds are broken apart into their individual ions when they are aqueous or dissolved in solution. Because, as we know, when ionic compounds dissolve, they get surrounded by water molecules as they form ion-dipole interactions. And so, when ionic compounds are dissolved, we write them as individual ions in an ionic equation. And then there's this thing called a net ionic equation where you then take the spectator ions and you cancel them out. And this is especially useful for representing precipitation reactions, which we'll be talking about soon. But precipitation reactions are where you mix two substances together where they're dissolved and then a solid forms and precipitates out. Because a net ionic equation is good for this because it really shows what's ultimately happening, which is two ions coming together, making something insoluble and precipitating out of solution. And just to define the term spectator ion, that's an ion that appears in solution as both a reactant and a product. It doesn't really do anything. In a minute, I'm going to toss you to a video where I go through all this that I made for my honors chemistry students. It's still great stuff as a review for you. But in there, I reference the solubility rules that are used in honors chemistry, which you may remember from your honors chemistry reference tables. That's these things right here. But you don't get solubility rules like that in AP chemistry, sadly. So all you need to know is some very simple solubility rules. Anything that contains sodium, potassium, really you can just remember it as group 1. That's lithium, sodium, potassium, rubidium, cesium, francium, if you ever had a compound with it, which you won't. And then ammonium, that's NH4+, and then nitrate, NO3. Those things are always soluble. That's the only solubility rule you really need to know for the purposes of this AP exam. That's straight from the College Board. That's all you need to know. So I'm going to toss you to that video. Take a look and see what happens. Today, we're going to talk about net ionic equations. And in order to get there, we're going to talk about what's first called a complete ionic equation. And so we're going to consider this reaction that's behind me on the board. It says lead 2 nitrate plus 2 potassium iodides make 2 potassium nitrates plus lead 2 iodide. And first of all, if we check the solubility rules, we'll notice that all nitrates are soluble. That's the first rule. So potassium nitrate is soluble. And then all chlorides, bromides, and iodides are soluble except silver, lead, and mercury too. So the lead 2 iodide is our precipitate. So we'll represent that with the letter S, meaning that it is solid or a precipitate that comes out of solution. So for a complete ionic equation, and you'll never have to actually write a complete ionic equation, you just need to know what these are. It shows all the particles in solution as they actually exist, where soluble ionic compounds are written as their individual ions. So if we go back and we look at this equation, well, lead nitrate, all nitrates are soluble. So we would break this apart into lead plus nitrates plus potassium ions plus iodide ions plus potassium ions, plus nitrate ions, plus the lead 2 iodide that stays together as a solid. So in other words, the complete ionic equation would say that lead with the plus 2 charge plus 2 nitrates plus 2 potassium ions plus 2 iodide ions makes 2 potassium ions plus 2 nitrate ions plus lead 2 iodide. Because all those other things would dissolve in solution. And with very few exceptions, these chemical reactions take place in solution. So that's a complete ionic equation. We pretty much never write these because of these things called spectator ions. Spectator ions are ions that essentially just watch, kind of like at an athletic event, spectators sit in the stands and watch. They generally don't go down onto the field or the court and participate in the game. That's a quick way to get kicked out of the game or arrested. So if we look at this, for instance, in our reaction here, the nitrates stay as part of the solution on both sides, and the potassiums stay as part of the solution on both sides. So potassium ions and nitrate ions are spectator ions, because what's happening in this reaction is that the lead is hooking up with the iodide to make lead 2 iodide. So the potassiums and the nitrates, they started floating around in solution, they finish floating around in solution. They're spectators. And so to get to a net ionic equation, what we will do is we will eliminate the spectator ions. So we'll take the nitrates and cross them out, and the potassiums and cross them out. And so our net ionic equation just says that lead 2 plus 2 iodides makes lead 2 iodide, like so. Now, essentially, for any double replacement reaction, all you do is on the product side, you have your precipitate, and on the reactant side, it's broken apart into its individual ions, right? So net ionic equations include only the ions that actually participate in the reaction, and we can write these for double replacement reactions that form precipitates or that form water. So I can show you a couple more examples of net ionic equations real quick. All right. If we take a look at this reaction, we have calcium chloride plus sodium sulfate makes calcium sulfate plus sodium chloride. If we check our solubility rules, we'll see that all sulfates are soluble except calcium, strontium, barium, mercury, lead 2, and silver. So calcium sulfate is our precipitate. So to write a net ionic equation, on the product side, we're going to have calcium sulfate. And on the reactant side, we just break it apart into calcium ions and sulfate ions. Because essentially, in this reaction, when you put it into water, the calciums and the chlorides dissolve, the sodiums and the sulfates dissolve, and your reaction is the calciums and the sulfates come together and precipitate out, making calcium sulfate. The sodiums and the chlorides remain floating around in solution. We'll take a look at one more example. All right, in this reaction, we have hydrogen chloride reacting with sodium hydroxide to make hydrogen hydroxide and sodium chloride. Well, if we check our solubility rules, it says all hydroxides are insoluble except for group 1, strontium, barium, and ammonium. And then we know that sodium chloride is soluble because it's in group 1. But hydrogen's not really in group 1. So is hydrogen hydroxide soluble? Well, it's kind of a trick question because hydrogen hydroxide is liquid water. And water doesn't dissolve in water. It's a key thing to remember. Water doesn't dissolve in water. When you put water into water, you just get more water. And if you produce water, that is a way to make a reaction happen. So what happens in this reaction is you have the hydrogens and the chlorides floating around, and the sodiums and the hydroxides floating around, and the hydrogen and the hydroxide come together and produce more water. So our net ionic equation produces water, and we break it apart as the hydrogens and the hydroxides that are what make this reaction happen. So I hope that this makes a little bit of sense to you. All right, and welcome back. What I do want to do, I want to walk you through just a couple of examples of some net ionic equations that we could write based on our knowledge of solubility rules and everything else. So for this reaction right here, we've got calcium chloride plus sodium hydroxide makes calcium hydroxide and sodium chloride. Now, we know that 3 of these things are soluble because it says right by them AQ, which means aqueous or dissolved in water. And then calcium hydroxide is our insoluble precipitate. So if we were told to write a complete ionic equation, we would break this apart into calcium ions plus 2 chloride ions plus a sodium ion. Actually, it's going to be, so I'm looking at this equation is not balanced either, so we need to put a 2 right there, a 2 right there. So 2 sodium ions plus 2 hydroxide ions. And that's going to make calcium hydroxide plus 2 sodium ions plus 2 chloride ions. And we don't break up the calcium hydroxide because it is a solid precipitate. So that would be a complete ionic equation. And then if we were to go to a net ionic equation, our chlorides are the same on both sides as are the sodiums. So our net ionic equation is just going to be that a calcium ion plus 2 hydroxides make calcium hydroxide. Right. And let's take a look at one more. This one, I don't tell you what is soluble and what's not, but this is where your only real solubility rule you need to know comes into play. So if I told you that a student observed a precipitate that formed, could you figure out what the precipitate is? Well, first of all, precipitates have to be a product, and we know that all potassiums and all nitrates are soluble, so this is soluble. So if a student observed a precipitate form, it has to be the other thing, which would be the silver chloride. So that would be our precipitate. If we were to write a net ionic equation for that, on the product side, we would have the silver chloride, and then we just break it apart into silver ions and chloride ions. So that would be a net ionic equation for that.